Welcome to Analog Instruments channel. Today in this lecture, we are going to discuss about LOCOS process. LOCOS process stands for local oxidation of silicon. It is a fundamental technique on semiconductor manufacturing. So, coming to discussion about the definition of LOCOS, as I earlier told that LOCOS stands for local oxidation of silicon. It is a microfabrication process used to grow in a thick layer of silicon dioxide on a silicon wafer, but only in specific selected areas. I'll show this where the specific selected areas in the coming part of the video. So the primary purpose is to electrically isolate different active components. Here active components means the transistor, two different transistor, two devices from each other on the same chip. So this insulating layer is known as field oxide. This is different from gate oxide. And coming to discussion of, yes, I think I'm audible and you can see the video here. So here in this video, I mean the layout thing, you can see that. So we have two different devices where these two devices don't share the OD because of the difference between the width of OD. So this will be placed with a proximal distance or the minimum DRC. So in such cases where these two transistors or the active devices needs to be isolated electrically, and the purpose of isolation I will be speaking. So the purpose of isolation, why the electrical isolation is crucial. So when you have two different devices here, the example might be some transmission or the receiver chip, two chips. So these chips might have antennas or some communication, electrical communication, crosstalk kind of electrical signals might be present in the end. But in our case, when I spoke earlier, in that case we have source and diffusion regions. So we can see under the OD layer, like oxide layer or thick oxide layer, in this under this oxide layer we will be having the diffusion layer. So this diffusion layer, there is a possibility of electrical interference between those two implicitly. Under the this diffusion layers are under the OD. When OD is shared, we will not have electrical interference, but when the OD is not shared, there is a possibility of electrical short or electrical connectivity between the two devices. Here we have the necessity of electrical isolation between the two different transistor or two devices. So coming to the LOCOS process flow, while orally speaking about the main three steps of the process, the initial three steps, we will be having silicon wafer. This silicon wafer will be consisting of a p substrate, substrate. In that N well will be there, and might be or might not be present of N well, and the diffusion regions, which are the more crucial part for which the LOCOS process is being carried out. And over the silicon wafer, there will be a pad oxide, which is also a silicon dioxide layer, but this layer is a very thin layer which is used to isolate the upcoming silicon nitride layer and the silicon wafer, to isolate them and to stress relieve the buffer. And over the pad oxide we will be having a silicon nitride layer. This is to isolate the substrate from the oxidation, where the gate oxide needs to be formed, and this is very crucial, that will be discussed later. So discussing about the process of LOCOS, you can say that I earlier told that we will be having a three layers. The sky blue one represents the silicon substrate, and over that we will be having a brown color pad oxide. This is a silicon dioxide, very thin layer, and this will be separating the top layer, that is silicon nitride, and the substrate. So that is the significance of the pad oxide. And we can see the process carried out wet oxidation at 900 degrees Celsius with 15 minutes to grow silicon oxide layer. This is for pad oxidation, 900 degrees for 15 minutes. This is for growing of silicon pad oxide. And over that we will be depositing the silicon nitride, that is uh, we will be using this formula to form the silicon nitride Si₃N₄, that is silicon nitride layer. And over that we will be forming the photoresist. The compounds of the silicon photoresist are shown in the chemical equation. And now this, there will be two process, that is photolithography and etching. So the process of photolithography we must be familiar, and this Photolithography includes some putting of mask where which will be mostly as the earlier compound I shown, and this will be a, very specifically, and this mask will be like that. After the exposition of UV light on the mask, the mask on the isolation region will become thin, will be so soften, and the photoresist over the non-isolation regions or where the local oxidation isn't required, there the mask will remain hard. And after this process, the silicon nitride under the softened photoresist or softened mask, which will be over the isolation region where the silicon oxidation needs to be grown, that will be removed by the process of etching. But and here the silicon nitride under the non-isolation region remains same, and this you can see in this process. You can see wafer you will be having pad oxide and or the silicon nitride carbon hard mask, that is the brown black color one. Over that we will be having photoresist. After that you will be having this edge trench and this kind of shapes, and cavities you can see, those are the isolation regions where we need to put the silicon oxidation, that is local oxidation. Now discussing about the LOCOS process specifically, after the formation of this isolation cavities, there will be a process of local oxidation. This is the main crucial step of the LOCOS process. This is the actual local oxidation process where this wafer is heated at 100,000 degrees Celsius for 19 minutes in H2O, that is water, which will be growing the 500 nanometers of silicon dioxide. So this process is called thermal oxidation. This is different from the gate oxidation, that will be a controlled process, but this isn't like that. This is a thermal oxidation process where the silicon dioxide will be forming in the isolation regions. But during this process, you can see that there is a deformalities in the silicon nitride at the edges of the isolation region. This will be leading to a bird beak effect. So now the bird beak effect. So I told that there will be deformalities formed in the edges, just edges of the isolation regions where the silicon nitride bends, and there will be oxide formed under this silicon nitride, which will be leading to deformalities in the shape of the formation of oxide. This will be some kind of circle similar to a bird's beak. So during oxidation, the oxide not only grows down but also laterally sideways under the silicon nitride. This create tapered oxide edge that looks like a bird's beak. This bird beak encroaches on the active area, reducing the usable space for transistor. This sentence means that after the completion of this oxidation, we have to remove the silicon nitride, and that site we should be filled with gate oxide. When we have another oxide under that with some different shape, the shape of the gate oxide that needs to be fabricated on that non-isolation regions will also change, and we will be having various specifications for gate oxide with widths and lengths. If that width and length are altered, there will be formation of parasitic capacitance and very uh, unnecessary effects on the working of transistors. So that is the main problem of this low cost process. So as I told earlier, this is the main disadvantage of the low cost process is bird beak effect. And when the size of the technology library or the size of the node goes below 25 0.25 micrometers, the even 0.1 micrometers also will be very crucial for manufacturing, the gate oxide length also will be decreasing, and this deformity region also will be very crucial. So the where the gate oxide need to be very precisely formed. That is the main disadvantage of low cost process, which cannot be used for 7 nanometers or very low technology nodes. This process cannot be used. And the advantages remains like there are simply low cost process, high quality robust thermal oxide, I already told that this is a thermal process, provide good surface planalization. So what is the successor of this process?